All right, so we talked about strengths of acids and whether an acid is strong or dangerous or not. But now we're going to move on to talking about what pH means. And really, pH measures kind of how strong or dangerous an acid can be. So strong acids are going to dissociate completely, which means they will have a lot of hydrogen or hydronium ions in solution. And also, if there's a higher concentration of them, they will also have more hydrogen or hydronium ions in solution. So what pH measures is pH means the power of the hydrogen ion. And remember that when we talk about hydrogen ions, we're talking about hydronium ions. Those two terms can be used interchangeably because remember, this doesn't actually exist. Hydrogen ions don't actually exist in solution. They're always hydronium ions. But just for simplicity, we're going to call them hydrogen ions. Okay, so how you compute pH is the negative log of the hydrogen ion concentration. Now, when you do this, let's say you had a molarity or a hydrogen ion concentration of 10 to the negative 8. How this works is you have the negative log of this, and brackets will mean concentration. Okay, so what's that pH? Well, how this works is log cancels with the powers of 10 and the negatives cancel. So you have a pH of 8. Now, here's the thing that's interesting, is if you have a concentration of negative 2 and you have a concentration of negative 8, this value right here is bigger, right? Negative 2 is a bigger number than negative 8. Well, with what I did right up here, you can basically see then that this will yield a pH of 2, and this one will yield a pH of 8. So what you can see is that this right here is more acidic. It has a higher concentration of hydrogen ions in it than this one. And so you may have learned in the past that if you have a pH scale, it goes from 0 to 14, right? 7 is neutral, and this is the acidic, and above 7 is the basic. Well, if you look back at these numbers, you can start to see that a little bit better, right? You can see that this is a higher concentration and it has a lower pH, and this is a lower concentration of hydrogen ions and has a higher pH. Okay, so that is helpful when you look at this pH scale where 7 is neutral, that's water. 14 would mean that it's 10 to the negative 14 hydrogen ions, whereas like a pH of 1 down here would be 10 to the negative 1. And 10 to the negative 1 is a much bigger number than 10 to the negative 14. So this pH scale is all based on how many of these guys you've got, okay? So that's important to remember when we're going through all of this. Okay, so this right here, this guy, is just one of the equations in this whole interrelationship. Okay, so we've kind of gone over this, and you will have my TI calculators available. And if you don't have one at your desk right now, you can use one throughout class. I recommend that you actually use them throughout the unit so that you get familiar with my yellow calculators. You punch things in, you know where all the buttons are, the log function, the negative, the parentheses, all that. Because these brackets here, which anytime you see anything with a concentration, that's what this bracket means, is hydrogen ion concentration, and you'll put it inside that. But on a calculator, you're just going to use that as a parenthesis. Now, another concept I want to introduce you to is POH, which is the power of the hydroxide ion. Has the same basic equation, except you might be measuring how much how many hydroxide ions are floating around in solution. And usually you might look at this when you see a base, for instance, something like NaOH, because when it dissociates, it gives off hydrogen ions. Or even more importantly, something like water, because when water dissociates, it gives off hydrogen ions and hydroxide ions. Okay, so you can get a pH from this ion and a POH from this one, which brings me to this equation right here. Okay, so this equation right here is Kw. Now, Kw represents this dissociation constant of water. Now, in water that's at room temperature and at sea level, this is the number you get, 10 to the negative 14. That number is calculated from the hydrogen ion concentration, right here, and the hydroxide ion concentration, right here. So what's important to kind of keep in mind when we're looking at this is, what's the pH of water? You might be familiar with the pH of water being 10 to the negative 7, the pH of water being 7. Well, I showed you earlier that a pH of 7 equates to a hydrogen ion concentration of 10 to the negative 7. And so if this always equals 10 to the 14, then that means that the hydrogen ion, or the hydroxide ion concentration must also be 10 to the negative 7, which kind of makes sense, because if you look at water in the equation that I just drew earlier, water, when it dissociates or splits apart, ionizes, I guess I should say, when it ionizes, it's going to create equal number of hydrogen and hydroxide ion concentrations. So that kind of makes sense as to why each of them would be an equal value. 10 to the negative 7 and 10 to the negative 7 is going to, when you multiply those together, remember when you multiply two numbers like this together, you add the exponents. So negative 7 times plus negative 7 is negative 14. And that's always the kW value. So if these equal each other, that also means that 14 is going to be the pH plus the pOH. Okay, so this gets a little confusing because you're like, well, how did you get that? How did I get that? Well, I showed you earlier because of this equation up here. Okay, if I use that equation and I solve for the pH of the negative log of 10 to the negative 7, as I showed you earlier, the log cancels with the 10 and the negative cancels with the 7, with the other negative. So I have a pH of 7. So basically, if I have this value of negative 7 here, that gives me a pH of 7. And the pOH, because it is the same type of formula here, is going to give me a pOH of 7, which means that you have 7 plus 7 equals 14. And in a neutral solution, that makes sense. Okay, so this is a really nice roadmap for all of these calculations. Now, if you're trying to get from pH to hydronium or hydronium or hydrogen ion concentration, you can go this way, and you can use this, like this equation, depending on whichever one you're trying to find. And if you're going from hydronium ion to pH, you're trying to find the pH, then you can use this equation. If you want to go from pH to pOH, you've got this equation here. You can plug in 1 if you know pH and solve for pOH and vice versa. And then for pOH right here to hydroxide ion concentration, you can basically use the equivalent of these over here. Now, this is an important equation to keep in mind, but because you usually have so many exponents between these two values, and remember this word, this 10 to the 14 come from, that's the dissociation constant, the kW of water at room temperature and atmospheric pressure. So that's how many ions basically you have floating around between the hydroxide and the hydronium ions. And remember, this is actually a hydronium ion, but use hydrogen and hydronium kind of interchangeably. Okay, so this is one where you can go straight from hydronium to hydroxide and vice versa. But this is so cumbersome and easy to screw up on a calculator that sometimes 3 easy steps is easier than one kind of tricky step. So I tend to avoid this step here. And if I have to go from hydronium ions to hydroxide, oftentimes I actually do all 3 of these steps instead of just this one step. Now you can do whatever you want. You kind of have the toolbox using this this roadmap, which will be on my whiteboard and should be there right now, but will be on there for several days as you practice. This is great for you to practice with, but it will not be available on the test. So use it now until you get good at these and get familiar and comfortable with the equations. I just realized I'm missing a little crossing there on the H. But you will have to make your own or just become comfortable enough with all these equations that you can maneuver yourself. Okay, so I'm going to do a few example problems and then you will be on your own. Okay, so here's an example problem. So for this one, I need to find the pH, but what I'm given is the molarity of a sodium hydroxide solution. So basically, it's a 1-to-1 ratio. When this dissociates, I get a sodium and a hydroxide. So it's a 1-to-1 ratio, which means that my hydroxide ion concentration is going to be the same as my sodium hydroxide. So I've got this, which means I can find, I can find my POH by taking the negative log of 0.0429. Okay, because this right here is my OH concentration. For this reason here, it is a 1-to-1 ratio, and this right here is the sodium hydroxide, which means it's also the hydroxide concentration. So once I plug that into my calculator, and I push the negative button, and I push the log function button, which I'm looking for right now. When I put in the negative log of this, I end up getting 3.69. Now, it doesn't ask for the POH, it asks for the pH, and that's this right here. And if you go to the table, you can see 14 equals the pH plus the POH. So if I take 14 and I subtract the answer from that, I am getting a pH of 10.3. And that would be my answer. Okay, so this one asks you for the hydronium ion concentration. And the hydronium ion concentration for this is basically using this equation. Okay, so you're given the pH, but what you have to make sure is there's a 1-to-1 ratio. So you need to know the formula for nitric acid, which is NO3, which means that when it ionizes, it gives you this. And this is a 1-to-1 ratio, so that means that we're good. Okay, we don't have to worry about doubling anything or having anything or anything like that. So really, that means that you're just going to plug in 10 to the negative 3.5 into the calculator. When you plug that into your calculator, you get 3.16 times 10 to the negative 4. Or your calculator may spit it out like this, so I just want you to be familiar. This is the same thing. Okay?